Hey folks, in this video we're going to be talking about the standard enthalpy of formation, not the standard enthalpy of reaction. Although they're related, let's talk about it. So I want you, dear viewer, to be able to define standard enthalpy of formation and also use that standard enthalpy of formation to calculate the enthalpy of reaction. Holy wow! And that's about it. So let's talk about enthalpy of formation. That's the energy that's absorbed or released when a compound, or an element in its non-standard state, is formed from elements in the standard state. So you get a little bit of carbon in the standard state, you get a little bit of sulfur in the standard state, you can mash them together and make some carbon disulfide. And from that, there will be a certain amount of energy either absorbed or released. That's going to be the delta H of formation, making something that is not in the standard state of pure elements. So another example is if you take hydrogen in the standard state, oxygen in the standard state, you mash them together to give you some H2O. The delta H of formation here is going to be the energy that's absorbed or released when you form this guy from pure elements in the standard state. Another example would be if you took hydrogen in its nice standard state as a gas, and you suddenly force that to become a solid, which would be really intense. That would be a reaction that would then release a forkload of heat. And so to do that, yeah, there would be a standard delta H of formation for forming this hydrogen in its non-standard state. Here's another example. If you wanted to make some sugar, you take all the elements in their standard state, mash them together. That's how you can get some sugar. And for this, there is a delta H of formation for figuring out how this would be formed if you combined all these elements together. So fancy science folks have determined the delta H's for many chemicals. Also, just to say, this is a reaction that probably wouldn't take place in nature. It's just going to go out and say that. It's the thing that we write down for doing these delta H of formation calculations. But science folks have determined the delta H's of formation for many chemicals. You can find these in fun reference tables. But why? Why is this useful? Why is this something that we can care about? Because like this isn't a reaction that actually happens in real life. You don't just mash carbon, hydrogen, oxygen together and suddenly get sugar. So why is this useful? Well, we can use our delta H's of formation to calculate the delta H of reaction, which was mentioned in our objectives. And so this is useful when you can't calculate the delta H or determine the, not calculate, but measure the delta H of reaction in a lab setting. So maybe it's a reaction that's like real scary and you can't safely measure it in a lab setting. Or maybe it's some wild reaction that's not easily recreated in a lab. You can use delta H's of formation to figure this puppy out. So one thing I have to say is if we're talking about the delta H of formation for pure elements in the standard state, it's 0. So if we look at this hydrogen in its standard state, its delta H of formation is 0, because that's how hydrogen wants to be. Or oxygen in its standard state as a gas, delta H of formation for that dude is 0. All right, let's talk about, here's another example. If you got some iron, you know, at room temperature, hey, little brick guy, go away. At room temperature, you're going to find iron as a solid, and its delta H of formation would be 0, because it doesn't take any energy for it to be in its standard state. It doesn't have to form itself. I don't know. It's a weird way of saying it. Anyway, let's talk about how we're going to calculate delta H of reaction using the delta H of formation. So in a reaction, it's helpful to think about, at least for me, that reactant chemicals are taken apart and they form pure products. So pure products, they form product chemicals, not pure. So we're forming products and reactants are taken apart, which is kind of like the opposite of formed. So I think that is like we got formed and then reactants get like a negative thing on them because they're like it's the opposite of formation. Anyway, that's helpful when we think about this equation that we're going to look at here. Holy cow, that looks spicy. The delta H reaction is equal to the sigma, a little sigma notation. Hopefully you're familiar with this guy. We'll talk about it though. For the delta H of product minus, that's what I was talking about, this negative sign, minus sigma delta H formation of reactants. So basically what this sigma notation means is it means the sum of all these things that we're talking about. And so we're going to take the sum of all the delta H's for our products, delta H of formation for our products, and subtract from that the sum of all the delta H's of formation for our reactants. It's a mouthful to get out there. And so one thing we have to do is account for coefficients in a balanced chemical equation, which like when do we not account for coefficients in a balanced chemical equation? So let's practice by determining the delta H of reaction for this guy. And one thing that we're going to need to do is reference our friends, the tables of delta H's of reactions. So we're going to need to look up our delta H's of reactions for these guys. But before we do that, let's just write down this equation the way it ought to look. So we're going to take the sum of the delta H's of formation for our products. So we'll need to take into account our coefficients as well. So I'm going to I'm going to say, all right, products minus reactants. We've got 2 CO2 and 3 H2O as our product. So I'll put those in parentheses and add those together. And I've got 1 ethanol and 3 oxygens, so as my reactants. So I'll put them together in their own little parentheses, and I'll subtract reactants from the product. So now what I can do is look at some reference tables, and here I've got a reference table, nice, and I can see I've got my ethanol, who's in there, cool, I can copy that down, my carbon dioxide, and who else do I need? Oh, some water, some H2O gas. Great. And you might be like, yo, bro, you also need to account for this oxygen. But remember, this is oxygen in the standard state. Oxygen likes to be a gas. So its delta H of formation should be 0. So now I can just plug those numbers that I got in. My delta H of reaction is going to be 2 times the delta H of formation of carbon dioxide plus 3 times the delta H of formation for water minus the delta H of formation for ethanol. Neat. And so that gives me a fun answer of, wow, that's a pretty big number. Negative 1,000. Negative 1,366.8 kilojoules per mole. So that's how we use it when we're calculating delta H of reaction using delta H of formation. We're going to need to use a reference table, and from there it's not too spicy as long as you remember products minus reactants. Let's look at one more problem, eh? So let's give this guy a shoot. Why don't you... Well, you don't have a reference table of your own, so maybe I should help out with that. Here, feast your eyes on this puppy. So, might not be too helpful. Let's talk about this one together. So, we've got a reaction here, and yeah, we're going to need to look at the delta H's of formation for our reactants and our products. But one thing you will not find in most tables is for ionic compounds, you might not find them directly listed there. What we're going to see is that for these things that are aqueous, we're actually going to split those up into their respective ion. So if we have 2 FeCl3s, that means we have 2 iron ions, and 3 times 2, so 6 chloride ions over here. And on this side, we're going to have 6 hydrogen ions and 6 chloride ions as well. Let's look at that. Wow. Wow. So we can split apart our ionic compounds. And what else we can do here is say, you know what, if we got 6 on this side and we're going to subtract 6 chlorines on this side, we could go ahead and be like, let's get rid of those. And you know what else we could do? We could get rid of our hydrogen because it's in its standard state. Hydrogen likes to be a gas. That's the standard state of hydrogen. So that's going to be 0. The same is true for iron as a solid. That's going to have a standard state of 0. And as I said, with those 2 chlorines, rather the 6 chlorines on either side in 2 locations. If we're doing 6 chlorines here minus 6 chlorines over here, those we can get rid of as well. So our delta H of reaction turns out is just going to be equal to the iron plus that hydrogen. And if we look back at our reference table, we can see those values. Here we've got iron 3 plus as negative 49, and we've got hydrogen as 0. So it turns out our delta H of reaction is just going to be dependent upon this iron ion. And so we get a nice pretty boy answer of negative 98 kilojoules per mole. So that one's a little bit spicy, but only because you have to know that if you're dealing with aqueous compounds, we're going to need to chop those up into their respective ions. Well, anywho, that's the end of this video. I hope you understand how the delta H of formation is going to be used to calculate delta H of reaction. And remember, it's only for situations where you can't measure that reaction directly. Anyway, ta-ta. Have a great rest of your life.